Good afternoon, everyone. So, in this session, we'll be starting with a new chapter that will be the kinetic theory of gases, right? So, we'll be discussing ideal gas equations and different laws for ideal gas in this unit, right? And we'll be also discussing about the postulates of kinetic theory. And then later, we'll be discussing about different types of speeds for an ideal gas, right? And their calculations. And then we'll move on to the thermodynamics portion, right? So we're beginning with the kinetic theory of gases, right? So kinetic theory of gases, it's a theory given for the ideal gases, right? So the first point about any gas we have surrounding us is that the motion of gas molecules is a random motion, right? It's a random motion. It's not in a particular direction. It can be in any direction, right? For any molecule, right? Or we can say the motion of gas molecules in a container or in a surrounding around us, right? It's always a zigzag motion, right? So apart from the translational motion of a gas molecules, right? Gas molecules always rotate as well. They also perform the rotational motion, right? And they also perform the vibrational motion, right? So these are the energies present in the gas molecules, right? It can be translational kinetic energy, right? It can be rotational kinetic energy because gas molecules also translate as well as rotate, right? And they also vibrate, right? So these are all types of kinetic energies which can be associated with these motions, right? So kinetic energy is the sum of all kinetic energies, right? Or we can say it's defined as the sum of kinetic energy of all molecules, right? And it is dependent on the temperature, right? It depends upon the temperature. Upon increasing the temperature of a container, let's suppose we have a container, right? We have a container. Let's suppose if we have a container here, right? And let's suppose kinetic energy, and in this container we have some gas, right? We have some gas molecules, right? We have some gas molecules. They are moving in random direction, right? So at this temperature T naught, they are having some kinetic energy Ke1, right? And now if we increase the temperature further, then upon increasing the temperature, the kinetic energy of the gas molecule is going to increase, right? Or we can say its kinetic energy of gas molecule is directly proportional to the absolute temperature, right? It's directly proportional to the absolute temperature, right? So the temperature of this gas container is actually increased, then the kinetic energy of these molecules is going to increase, right? Or we can say the sum total of all the kinetic energy for this gas will actually increase, right? It will have a different kinetic energy now, and this kinetic energy will be greater than the initial kinetic energy, right? It will be greater than the initial kinetic energy. So the kinetic energy of gas is actually the sum of all the kinetic energy of all molecules, right? Upon increasing the temperature of gas, right, the kinetic energy of the molecules increases, right? So this is the basic idea of how actually the gas molecules move in a container or in a space, right? And there are different types of energies associated with the gas molecules, right? So the gas molecules, practically speaking, do also have the potential energies associated with them, because we know that there is always intermolecular force of attraction between the gas molecules, right? There is always intermolecular force of attraction between gas molecules, right? Or gas atoms, right? Thus, if there is intermolecular force of attraction between gas molecules, right, or we can say there can be the gravitational attraction between the gas molecule as well, right? So definitely every molecule have then some potential energy associated with it, right? So larger the intermolecular forces between them, right? Greater intermolecular forces between them, or we can say if the repulsive force is greater between them, then the potential energy less will be the potential energy, right? Or by magnitude, or we can say the greater will be the magnitude of potential energy, or we can say if the intermolecular force of attraction between them is greater, then the potential energy between them will be more negative, right? Or we can say it will be more in terms of the magnitude of potential energy, right? So greater the intermolecular force of attraction between the molecules, greater will be their potential energy, right? Or we can say that the two molecules will have greater force of attraction, right? So this is with respect to the gas, which is practically around present around us, right? There is always some forces, intermolecular forces, gravitational forces, and there can be other forces as well, right, between the gas molecules, right? And because of all these forces, the gas molecules in a container or surrounding us have some potential energy, right? It will have some potential energy, right? Now, let's talk about the total energies present in the gas, right? That's what we call as the internal energy of a gas, right? So, internal energy of a gas at a given temperature, it's actually defined as the sum total of all energies, right? The gas can have sum total of potential energy and the kinetic energy at a given temperature. And this energy of a system or of an object, that's what we call as internal energy of an object, right? Or we can say the internal energy of a gas, right? Let's talk about for solid, liquid, and gas, right? Internal kinetic energy is same for all, right? It depends upon the motion of molecules, or it will depend upon the motion of the molecules or atoms in a solid. It will depend upon the motion of atoms or molecules in liquid, and similarly, motion of atoms or molecules in gas, right? So internal kinetic energy has the same behavior, right? So if we increase the temperature, if we increase the temperature of a system, be it solid, be it liquid, be it gas, right, then definitely the thermal agitation or the thermal energy of the molecules of different materials, be it solid, liquid, or gas, right, it can increase, right? It will increase upon increasing the temperature, right? The internal kinetic energy of the molecules will increase, right? So that we say that the internal kinetic energy shows the same behavior for all the three types of matters, right? That's solid, liquid, and gas. Now, talking about the internal potential energy, right? Internal potential energy will be zero for an ideal gas, right? The property of an ideal gas is that, according to the kinetic theory, we assume that the force of attraction or any type of force, be it intermolecular force, right, or gravitational force between any two gas molecules, it is assumed to be a zero, right? It is assumed to be zero, right? If there is no force of attraction between the two molecules of a gas, then we cannot talk about the potential energy of that gas, right? We will not talk about the potential energy of that gas, or we can say that the potential energy of that gas is equal to zero. And this is the property of ideal gas, right? It's not a property of real gas. Practically speaking, there is always some gravitational force, or there is always intermolecular forces between the molecules of a gas, right? So practically, this situation is not possible to have an ideal gas, right? All the gases present around us are the real gases, right? They have some potential energy with them, right? But talking for the ideal gas has the intermolecular force equal to zero, gravitational force is equal to zero, or we can say the potential energy for the ideal gas is equal to zero, right? And this is minimum for the solids, right? It's minimum for the solid, right? So potential energy will be minimum for the solid, right? And the internal energy will be maximum for ideal gas and minimum for solid, right? So this is the important thing with respect to the internal energy, right? So gas molecules have both the kinetic energy as well as potential energy. But if we talk about the ideal gas only, right, then ideal gas has the potential energy equal to zero, or we can say the total internal energy of a ideal gas is equal to the kinetic energy only, right? So this is for the ideal gas only, right? Now let's talk about the basic postulates of an ideal gas, right? What are the basic postulates of ideal gas, or according to the kinetic theory of gases, right? So every gas consists of extremely small particles, right? That's known as molecules or atoms, right? The molecules of a given gas are identical but are different than those of another gas, right? So it says that if you have particular first postulate says that uh, every gas consists of small particles, right? And these particles we call as atoms or molecules, right? And each and every atom or molecule of a given type of gas. Let's suppose we have a hydrogen gas. We can have oxygen gas. Let's suppose talk about the helium gas or hydrogen gas only, right? then each and every molecule of hydrogen, right? Each and every molecule of hydrogen will be identical, right? But it may not be identical with the molecule of another gas, right? It will not be identical to the molecule of another gas. Let's suppose oxygen, right? So the oxygen gas molecule will not be identical with the hydrogen gas molecule, but each and every molecule of hydrogen gas or each and every molecule of oxygen gas will be identical, right? It will be identical, right? And second postulate is that the size is negligible, right? The size of the gas molecules or the gas atoms, right, is negligible in comparison to the intermolecular distances, right? Let's suppose the intermolecular distances of a gas molecules is of the order of nanometers, right? 10 to the power minus 9 meters, right? It's of the order of nanometers. Then the size of these gas molecules are very negligible, right? We can say that the size of the gas molecules is almost, we can neglect that as compared to the intermolecular distances between the two molecules, right? This is the second important postulate with respect to the kinetic theory of gases, right? And the third important postulate is that since we know that gas molecules are in random motion, they are in random zigzag motion, right? So the gas molecules, if we place a gas molecules or the gas, let's suppose some amount of the gas is placed in this container. Let's suppose hydrogen gas is placed in this container, right? So H2 gas is placed in this container. Then the molecules of this hydrogen gas will be in a random motion, right? The molecules of this H2 gas will be in a random motion, right? They will be in a random zigzag motion, right? And during this random motion, these gas molecules will not only collide with each other, but also with the walls of the container, right? So we can say that gas molecules are in continuous collisions, right? The gas molecules continuously collide with different objects or they continuously collide with each other as well as the walls of the containing vessel, right? Uh, Now talking about these collision, it's assumed to be the collisions to be perfectly elastic. It means that whatever the kinetic energy of the gas molecule was before the collision, same will be the kinetic energy of gas molecules after the collision. Or we can say that the energy of the gas molecules will not change. If the energy of the gas molecule does not change and the total energy of the gas molecule is kinetic only, right? Then we can say that because of the collisions, right? Because of the collisions between molecules or between the molecules and the walls of the container, the temperature of the system will remain same. The temperature of the container will not change unless we change the temperature externally, right? So because the kinetic energy does not change, if the kinetic energy does not change because of assumption that collision is perfectly elastic, then the temperature will remain a constant for the container, right? Or the gas present in the container, right? Otherwise, if the collision is inelastic collision, then there will be continuous loss in energy because of the collisions, right? The kinetic energy of the gas molecules will decrease, right? Continuously. The kinetic energy of the gas molecules will decrease, or we can say the temperature of the system will continuously decrease, right? So this assumption is an important assumption that the collisions are perfectly elastic, right? The total energy before collision will be equal to the total energy after the collision, and the total energy is here, it is purely kinetic energy, right? Or we can say the temperature of the system will not change because of the perfectly elastic collisions, right? So there will be no attractive forces or repulsive forces acting between gases, right? There will be no intermolecular forces between the gas molecules. And one more point is that there will be no gravitational force of attraction among the molecules as well. So if there is no attractive force, if there is no attractive force and not only attractive force, if there is no attractive force between the gas molecules, right? Or gravitational force of attraction among the molecules, right? It is assumed to be ineffective due to very small masses and very high speed of molecules, right? Gas molecules move with a very high speeds of the order of 10 to the power 6 meter per second, right? Or 10 to the power 7 meter per second. So this is the order of the speed of the gas molecules, right? So because of that, because of the negligence, or we can say if we neglect the gravitational forces or the attractive or repulsive forces between the gas molecules, you can say the potential energy of the molecules will be zero, right? If the potential energy of the molecule will be zero, then the total energy of the gas or the total internal energy of the gas will be purely kinetic, right? It will be purely kinetic, right? So molecules constantly collide with the walls of the container, right? Due to which they bounce back from the walls, right? It means that the momentum of the gas molecule changes, right? If there is a change in momentum, then we can say that gas molecule exerts some force, right? Some force, because if the momentum of the gas molecule changes, then there is definitely some amount of force applied by the container on the molecules, and the same amount of force will be applied by the molecules on the container, right? So, or we can say there will be definitely some pressure on the walls of the container, right? There will be definitely a constant pressure on the walls of the container, right? So that's these are some of the important postulates, right? Important postulates of the kinetic theory of gases. So the first postulate is that the gas molecules consist of small particles known as molecules, right? And all molecules of a given gas are identical, right? The second is that the size of the gas molecule is negligible as compared to the intermolecular distances between them, right? The third is that these gas molecules are in random motion, continuous random motion. They collide with the walls of the container as well as with the molecules, right, present in the container, right? And these collisions are actually perfectly elastic, right? It means that the total energy before for the gas molecule will be equal to the total energy after, or we can say there will be no loss in energy, or we can say that the temperature will remain same for the container, right? Temperature will not change for the container, right? Because of the no loss in energy, and there is no attractive force or repulsive forces between the molecules, and gravitational force of attraction between the molecules is assumed to be zero or negligible, right? Because of their high speeds and small masses, right? Because of their high speed and small masses, the gravitational effect is assumed to be zero, right? So because of that, the total energy of the gas molecules will be purely kinetic only, right? Purely kinetic. And because of the collision of these gas molecules with the walls of the container, the momentum change for the gas molecules, it means there's some force exerted by the walls of the container on the gas molecules, right? And then there has to be equal amount of force on the walls of the container because of the molecules, right? It means that there is some constant pressure on the walls of a container, right? So these are some of the basic and fundamental postulates of the kinetic theory on which our ideal gas will be based, right? So a gas following all these postulates, right? That's what we call as ideal gas, right? So for an ideal gas, there will be no force of attraction between them, between the molecules of an ideal gas, or we can say for an ideal gas, the total energy will be purely kinetic, right? And there will be some constant pressure applied by the ideal gas because of the collision with the walls of the container, right? And we'll define all these things for the ideal gas in terms of an equation that we call as equation of state for an ideal gas, right? Now let's talk about the ideal gas, right? So ideal gas, which follows the kinetic theory as well as all gas laws, right? And gas equation at every possible temperature and pressure. That's what we call as ideal or perfect gases, right? Ideal or perfect gases, right? So the equation that actually govern the behavior of the ideal gas, that's what we call as the equation of state for ideal gas, right? So let's suppose that so the equation of state, writing the equation of state for the ideal gas, that's nothing. That's if P is the pressure, V is the volume of the container in which the gas is present, right? Then PV has to be equal to nRT, right? This is nothing. This is the ideal gas equation, right? This is ideal gas equation. And any ideal gas has to follow this equation. That's PV equal to nRT, right? Where P is nothing. P is the pressure, right? And V is the volume. It's the volume of the container in which the gas is present, right? P is the pressure exerted on the walls of the container, right, by the gas, right? N is equal to number of moles of gas, number of moles of gas. And T is the temperature, right? T is the temperature of the container in which the gas is present, right? So P is the pressure exerted by the gas molecules on the walls of the container in which the gas is present, right? P is the volume of the container in which the gas particular gas is contained, right? N is the number of moles, T is the temperature, and we're left with R. R is called as gas constant, right? It's nothing, it's called as gas constant, right? And its value is 8.314, right? Joules per mole per Kelvin, right? Per mole per Kelvin. So this is the SI unit of this gas constant R, that's equal to 8.314, right? Joules per mole per Kelvin, right? So talking about the N, that's the number of moles of gas. Number of moles will be nothing. It will be defined as, let's suppose if we have to find the number of moles, right, of a given gas, that is given mass of a gas, right, upon the molar mass, right? Molar mass. The molar mass is nothing. It's the mass of the Avogadro number of particles, right? It's the mass of the Avogadro number of particles of a given gas, right? So Avogadro number is denoted by Na, which is nothing, which is 6.023, right, into 10 to the power 23, right? If this number of atoms or molecules of a given gas are present, right, then we say it's equal to 1 mole, right? It's nothing, it's equal to 1 mole, right? So these are the 1 mole of the particles, right? So the mass of these number of molecules of a given gas, or the mass of these number of atoms of a given gas, right? That will be called as a molar mass, right? That will be called as molar mass, right? For example, we have H2, right? H2, right? H2 gas, right? The mass of one atom of hydrogen is 1 gram, and the mass of two atoms of the hydrogen will be 2 grams, right? So it will be 2 grams for the mass of 1 mole of hydrogen molecules, right? The mass of 1 mole of hydrogen molecules will be 2 grams, right? It will be 2 grams, right? So in this 2 grams, right? In this 2 grams, we will have 6.023 into 10 to the power 23 molecules of this hydrogen gas, right? This number of molecules will be there, right? So we can say that 2 grams of the hydrogen molecule actually contains 1 mole of the hydrogen, 2 gram of the molecule hydrogen molecules contains actually 1 mole of the hydrogen molecules, or we can say 6.023 into 10 to the power 23 molecules, or we can say Avogadro number of molecules, right? So the molar mass is nothing, it's the mass of a given gas, right? Having the number of molecules equal to Avogadro's number, right? That's 6.023 into 10 to the power 23, right? So this is how we define as the molar mass, right? Then if we have to calculate the number of moles, right? Then it will be given mass upon the molar mass, right? Let's suppose we have 1 gram of hydrogen, right? 1 gram of hydrogen molecule, right? Then the number of moles of this 1 gram will be nothing. It will be 1 gram upon the molar mass, right? Given mass upon the molar mass, that will be 2, right? It will be half mole, right? Half mole. It means it will have the half the number of particles, half the Avogadro number of particles, right? Or half the Avogadro number of molecules of hydrogen molecule, right? So this is how we actually calculate the molar mass, right? Similarly, if we have helium, right? Helium gas, right? Helium gas. We know the helium gas for Avogadro number of particles of a helium gas, right? That will be the weight of Avogadro number of particles of helium gas will be equal to 4 grams, right? It will be 4 grams, right? Or we can say molar mass of helium is nothing, that's equal to 4 grams, right? 4 grams. It means that the 1 mole of the helium atom will consist of Avogadro number of particles, or the weight of those Avogadro number of particles will be 4 grams, right? Similarly, if we have 2 grams of helium, right? 2 grams of helium, then the number of moles of these 2 gram of helium will be 2 upon 4. It will be once again half mole, right? It will be once again half mole. Or we can say that 1 gram of hydrogen molecule will contain the same number of particles as that of 2 grams of helium, right? So the 1 gram of hydrogen molecule will have the same number of particles, right? Or same number of molecules as that of atom present in 2 grams of helium, right? So this is how we can find out the. Similarly, we have oxygen, right? O2, right? The mass of the oxygen atom is actually 16, right? 16 atomic mass units, right? And the mass of oxygen molecule will be 32 atomic mass unit, right? Or we can say the 32 grams of oxygen molecule, 32 grams of the oxygen gas will contain actually 1 mole of the oxygen molecules, or it will contain actually the 1 Avogadro number of oxygen molecules, right? So this is how we define the molar mass. So the molar mass of oxygen will be 32 grams, right? It will be 32 grams. So 1 mole of the oxygen molecule will have weight equal to, or the mass equal to 32 grams, right? So this is how we define the N, right? That's the number of moles, right? Now let's calculate a volume of 6 moles of carbon dioxide gas at NTP. NTP is normal temperature and pressure, right? So its normal temperature will be around 27 degrees centigrade, right? And the pressure will be 1 atmosphere, right? So it will have a temperature of 27 degrees centigrade and the pressure of 1 atmospheric pressure, right? So we have to calculate the volume of 6 moles of carbon dioxide, right? Gas, right? So any ideal gas, right, which is at NTP, right? Any ideal gas which is at NTP. So any ideal gas at NTP has to have the volume equal to 22.4 liters, right? So let's suppose we use this equation PV is equal to nRT, right? PV equal to nRT, right? And let's suppose we put n value equal to 1, right? Then we have to calculate the volume at NTP. So volume at NTP will be nothing RT upon P. You put this value of NTP here, right? NTP here, well, temperature here, right? At NTP pressure, pressure at NTP, that's 1 atmosphere, right? Then the volume will be equal to, volume will come out to be equal to 22.4 liters, right? Be it any gas, right? It doesn't matter whether it's a carbon dioxide, whether it's a oxygen, whether it's a helium, right? Or any other gas. So if the gas is at NTP normal temperature pressure, then the volume of 1 mole of that gas, irrespective of the nature of that gas, irrespective of the type of that gas, right? Provided that's an ideal gas, right? That's assumed to be an ideal gas, then the volume occupied by that gas has to be 22.4 liters, right? Has to be 22.4 liters. So it means that if we want to keep a 1 mole of any gas at NTP, right? At NTP, then the minimum volume required for that gas contained in a container is actually 22.4 liters, right? So if we have to contain 1 mole of gas at NTP, then we have to provide the volume of container at least equal to the 22.4 liter. Then it will only be possible to have a gas at NTP, right? Otherwise, it will not be possible, right? So we have to calculate volume of 6 moles of carbon dioxide gas. Now we have to calculate this volume of 6 moles of carbon dioxide gas, right? So 1 mole contains 22.44 liter of the container, right? So 6 moles at NTP will actually occupy the 6 times this volume, right? So 1 mole of gas, of any gas, it doesn't matter whether it's a carbon dioxide or oxygen or helium or hydrogen, any gas, 1 mole of any gas will contain 22.4 liters of the volume at NTP, right? At NTP. At NTP, it will contain 22.4 liters of the volume of the container, right? Now, if we have 6 moles of any gas, right? 6 moles. 6 moles. So we have to actually provide 6 times 22.4 liters for the gas to be at NTP once again, right? To be at NTP, right? So it will be equal to 6 multiplied by, it will be 2, right? So 132 plus 2.4, right? It will be 134.4 liters, right? 134.4 liters. So this much of volume will be required for the 6 moles of carbon dioxide. Even if we mix different natures of the gases, right? For assuming all the gases will to be ideal, right? Let's suppose we have 1 mole of oxygen, 1 mole of hydrogen, 1 mole of carbon dioxide, right? 1 mole of helium, right? So we have each mole of six different gases. Then combine them together, we have the six moles, right? Six moles. Then if we want to have the if we want to keep them at NTP, then still this much of volume will be required, right? This much of volume will be required, right? At NTP, right? That's 134.4 liters, right? Now the next question is that calculate pressure exerted by 3 moles of an ideal gas, right? Kept in a vessel of volume 6 liters, right? Calculate pressure exerted by 3 moles of an ideal gas kept in a vessel of volume 6 liters at 27 degrees centigrade, right? At 27 degrees centigrade. So we have to calculate the pressure. So using ideal gas equation, right? PB is equal to nRT, or pressure will be nRT upon V, right? Now there are 3 moles of the gas, right? Let's suppose if we calculate the pressure in terms of atmosphere, then we will take the value of R equal to 0.0821, right? So this will be the value of R. Multiplying with the temperature, that will be 300 kelvins, right? Upon the volume, right? Upon the volume. The volume is 6 liters, right? 6 liters. So the pressure has to be approximately equal to, it will be 0.0821 multiplied by 300, right? Upon 2, right? Upon 2. So it has to be, okay, it has to be 8.2 into 3 upon 2, right? 3 upon 2. So it will be 4.1, right? So it will be 12.3 atms, right? So this should be the pressure of the gas, right? 12.3 atmospheres, right? This much of the pressure will be there for the gas, right? For the 3 moles of an ideal gas in the container, right? Now let's move on to the different laws of the gases, right? Which actually is being followed by the ideal gas, right? So the different laws followed by the ideal gas, right? And we will study these laws one by one, right? Let's begin with the two famous laws. That's first is the Boyle's law, another is the Charles law, right? So according to this law, for a given mass, right? If we fix the given mass of an ideal gas at constant pressure, right? At constant pressure, then the volume of a gas will be actually directly proportional to its absolute temperature, right? That's the Charles law, right? That's the Charles law. So the Charles law says that if we have a given amount of, or a fixed amount of a gas, of an ideal gas, right, at constant pressure, kept at constant pressure, then volume of a gas will change according to the temperature, or we can say the volume of a gas will be proportional, directly proportional to its absolute temperature, right? It will be directly proportional to its absolute temperature. So volume of a gas will be directly proportional to the absolute temperature. V will be directly proportional to T, or we can say at constant pressure, right? At constant pressure. At constant pressure. So volume will be directly proportional to the temperature, or we can say V1 upon V2 will always follow for the ideal gas at constant pressure. That's equal to T1 upon T2, right? So this equation will be always followed by an ideal gas, right? At constant pressure, right? That's V1 upon V2 will be equal to T1 upon T2, or we can say uh, V upon T has to be a constant, right? V upon T has to be a constant, right? So V upon T has to be a constant. Now, if we plot a graph between, volume, right? Volume and temperature, right? Volume and temperature, keeping pressure as a constant, right? Now, this temperature is actually here in Kelvin, right? It's actually in Kelvin. So the graph has to be a straight line passing through origin, right? It will be a straight line passing through an origin, right? So this will be the uh, graph for a Charles law, right? Followed by the ideal gas, right? Provided the temperature is taken in Kelvin scale, right? Then it will be a graph straight line passing through the origin, right? And similarly, if we plot a graph between volume upon temperature versus temperature, right? So volume upon temperature versus temperature, right? Provided the pressure is a constant, right? Pressure is a constant. We know that V upon T is a constant here, right? V upon T is a constant, right? So it will be a straight line parallel to the x-axis or temperature axis, right? It will not change at all, right? because it's a constant, v upon t is a constant, right? It has to be a straight line parallel to the x-axis, right? Now let's suppose that we are taking the temperature in the centigrade scale, right? We know that in Kelvin scale, right? In Kelvin scale, that's equal to 273 plus temperature in centigrade scale, right? So 273 plus temperature in centigrade scale gives the temperature in a Kelvin scale, right? So it means that if we have to plot between the volume versus temperature, right? Let's suppose V is proportional to T, or we can replace it with the constant K. So V will be equal to KT, right? But KT has to be in a Kelvin scale here, right? Let's suppose it's not in Kelvin scale, it's in centigrade scale, right? You can write it T degree centigrade plus 273, right? 273. So you can see here we can have this equation that's kt, right? Kt plus k times 273, right? K times 273. Now you can see here we can rewrite this equation. We can rewrite this equation in this form, right? V will be actually equal to it will be a constant kg, right? Kg, and let's replace this another k times 273 degree 273, right? With another constant c, right? Now let's now plot between the volume versus temperature, right? Now the temperature here is in degree centigrade. If we plot a graph between volume and the temperature, you can see it actually follows an equation of a straight line. That's y is equal to mx plus c, where c is the intercept here, m is the slope of this line, right? M is the slope of this line, right? So volume versus temperature graph, right? Now you can see here the intercept of this graph is a positive intercept, right? It's a positive intercept, right? Having a positive slope, right? Positive slope with positive intercept. Or we can say that this graph will start from the y-axis, right? With some intercept here, right? And it will be a straight line, right? It will be a straight line. So this temperature has to be in degree centigrade, right? So the graph between volume versus temperature depends upon it will be a straight line for both the cases, but whether it will be passing through origin or not, it depends upon the scale of temperature on which we are calculating the or rating the temperature of a given gas, right? So if it is in Kelvin scale, then it has to be a straight line passing through the origin, or if it is in degree centigrades, then it has to be a straight line having some intercept, right? Having some positive intercept, right? It will definitely have some positive intercept, right? So this was the graph for the Charles law, right? Now let's discuss the Boyle's law, right? So the according to the Boyle's law, right? For a given mass of an ideal gas, if the temperature of the given mass of an ideal gas is constant, then the volume has to be inversely proportional to its pressure, right? It has to be inversely proportional to the pressure. Or we can say if the temperature of a given mass of gas is fixed, then the pressure will be inversely proportional to the volume, right? It will be inversely proportional to the volume, right? So we can say that P will be inversely proportional to volume V, right? At constant temperature, at constant temperature. At constant temperature, P will be inversely proportional to the volume, or we can say that PV has to be a constant, right? PV has to be a constant. If PV is constant, then we can write it as P1 V1 has to be equal to P2 V2, right? So this is an equation for an ideal gas which is at constant temperature, right? Which is at constant temperature and follows Boyle's law, right? It will follow Boyle's law. So Boyle's law is nothing. If we increase the pressure of a gas, then the volume has to decrease, right? Or if we decrease the volume of a gas, the pressure has to increase at constant temperature, right? So the Boyle's law simply states that pressure is inversely proportional to the volume, right? Provided the temperature of a given gas is a constant, right? Or we can say at a constant temperature, pressure of a given gas is inversely proportional to the volume, or we can say PV is a constant, or we can write it in this way that P1 V1 has to be equal to P2 V2, right? Now let's plot the graph between the pressure and the volume, right? Pressure and the volume at constant temperature, right? Pressure and the volume at constant temperature, right? if you plot a graph between pressure and a volume at constant temperature, so we can write this equation. P will be actually constant upon the volume, right? Constant upon the volume. You can see here, as the volume tends to infinity, right, then the pressure approaches to zero, right? Or we can say if the volume tends to zero, then the pressure approaches to infinity, right? So the behavior of this graph will be like this, right? It will be a hyperbolic behavior, right? It will be a hyperbola, right? It will be a hyperbolic graph between the pressure and the volume, right? So this is how the behavior of graph will be, or the pressure versus volume graph will be for the ideal gas, or we can say it will be a pressure versus volume graph for a Boyle's law at constant temperature, right? At constant temperature. Now, if we have to plot between pressure versus 1 upon volume, right? Pressure versus 1 upon volume, right? In that case, we can say that pressure versus 1 upon volume, right? Let's replace this 1 upon volume with uh, 1 upon v. We can replace it with x, right? Then p will be equal to kx, right? So you can see here it will be a straight line, right? It will be a straight line but passing through the origin, right? With zero intercept, right? It will be a straight line passing through the origin with zero intercept. So this will be the graph between pressure versus 1 upon volume, right? So this is the graph between pressure versus volume, and this is the graph between pressure versus 1 upon volume for an ideal gas, right? At constant temperature, right? So summarizing the two laws which are being followed by the ideal gas, first is the Charles law, another is the Boyle's law. So the Charles law simply states that the volume will be proportional to the temperature at constant pressure. If we increase the temperature, the volume will increase. If we decrease the temperature, the volume of the gas will decrease, right? Similarly, Boyle's law states that proportional pressure is directly or inversely proportional to the a volume of a given gas, right, at constant temperature, right? So if we increase the volume, the pressure will decrease. If we decrease the volume, the pressure will increase, right? So that's it. That's the two laws for the ideal gas. Then there is third law, Gay-Lussac's law, that will be discussed in the next lecture, right? And we'll be also discussing different types of velocities or speeds for a ideal gas, right? That will be done in the next lecture. Till then, take care and goodbye.